All right, seeing a few people show up. Hopefully y'all can see my screen and you should be able to see some notes. Should make this a little bigger for now. Good morning, everyone. Just kind of letting things get settled. If anyone could just kind of pull up the chat and just make sure that you can see my screen, give me a yes. And cool, awesome. This is only the second time I've done it. I just finished my 8 a.m. class. I did some dry runs last week and had a couple hiccups, but I think things are going to go mostly well. The biggest issue I have occasionally is transitioning from a whiteboard and back to my screen. If anyone can ever not see something, if I'm talking like you should see something on the screen, just let me know. So welcome to the new world. This is going to be an interesting experience, especially for us, given that, I mean, how is it we usually run things in class? I talk for a little bit and then let y'all work in groups. But in today's world, group work is not exactly encouraged, at least face to face. So we're going to have to do some things different. And I had mentioned in those emails that there would be discussion boards posted in Canvas, and I do expect participation. I don't need someone to write 50 or 60 different things, 50 or 60 different posts. Now, if you do, if you want to contribute that much, that is excellent. As hopefully you have good ideas. But I'm just going to look for participation here and there. I don't want to really set a hard number to it yet. It just kind of like with class, I don't say, oh, if you don't do this, you're not going to get 100. It's just I want to see everybody trying a little here and there. So if I have to put stricter details on that, then I will. But I'm just hoping that everyone in the spirit of things will openly participate, whether it's asking a question or giving an answer. I'm not going to say, oh, you never gave any answers, so you didn't participate. If you ask questions, that's participating. If you give answers, that's participating. So it can be on either side of things. I unfortunately am extremely busy getting things done ahead of time for all 5 of my classes, all unique classes. So I'm a little behind on setting up any discussion boards for us. I'm going to try and get that done tomorrow, at least get 1 or 2 set up. And they could be about a problem I post in the discussion board. They could be about a problem from your worksheets. It could be about something from the notes. It could be about a specific homework problem. It could be anything. So just please be aware that the discussion boards are coming. Also, as a reminder, let me just pull up something. As a reminder, our midterm will cover chapters 1 through 4, which we finished 4.1. It feels like a month ago, but it was just a few weeks ago. 4.1 was the last thing that we covered in class, so we still have to cover 4.2, 4.3, and 4.4. So once we finish 4.4, I will give you your midterm review. I lost my train of thought. So after I give you your midterm, then the test will be posted in my math lab. So it's going to feel like a homework assignment in that it's posted in my math lab, but it's not going to be like a homework assignment in that you must complete it in one sitting. So once you start your test, you need to be prepared to sit down for roughly 2 hours. I normally only make this a 75-minute test, but given that it's at home, it's going to be either 90 minutes or 120 minutes, depending on a few variables, because I'm going to change some things around. But I want to make sure I give you a little more time since you have to type in your answers instead of just writing them down. Partial credit is going to be very, very, very difficult and unlikely in almost every situation. You're going to be taking your tests at home. I can't guarantee that you're not looking at notes or anything else that's suspicious. And I don't know if, oh, okay, they finished their test and they got let's say a 40. And you just go back on the paper where you showed your work and you just change things and you erase and put other answers up there. And then, well, Mr. Beckner, I had all the answers right on my paper, but I just typed them all terribly in my math lab. So I don't really want to have to deal with that kind of scenario. So again, partial credit is going to be very, 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 very rare for the test. But I will give you 2 attempts on the midterm to kind of balance things out, where I'm trying to find fairness when I can and strictness when I have to. So it's not just going to be one day for the midterm. It will be posted for at least 3 days, maybe 4, but 3 or 4 is what I'm thinking. And you'll of course get a week's notice. When I give you the review, I'm likely to post the test the next class. So let's say I gave you the review on Monday, then I'll post the test on Wednesday. Or if I gave you the review on Wednesday, then I'll post the test on Monday. And I don't know which is going to happen yet because things are going to flow very differently. I expect that we're probably going to not finish as much material as I would like, but there's certain things I really, really want to get to that are even more important right now. As some of you may know, our stock market is, we're in a bear market right now. Things have pulled back because of investors not being very confident in a lot of our businesses, especially restaurants, things like that have to close or are just doing a delivery service right now. So when people have their reservations, they don't want to have their money in it because things are going to go down more potentially. But the funny thing is, even though investments are going down, it's an excellent time to be buying in because you're basically getting things on a discount. So what's the point of this rant? I still want to talk about things in Chapter 9 because they're very important. If I find that we're running low on time, we've already lost a week. This is going to be a longer process doing this digitally now. If I find that we're running low on time, I may skip something from Chapter 7. I may skip something from Chapter 8, just so that we can still talk about investing, buying houses, retirement planning, at least on a basic level to give you ideas. Your project is still due the same day, which I believe, oh no, I can't remember. Was it the 6th or the 7th or the 8th? It was the first week of April. I know I posted that in the email, so see email. I just can't remember off the top. 8th, someone just said the 8th. So I'm going to go with that. That sounds correct because that was me giving you an extra week after finishing it. So budgeting also is something very, very important right now when we're dealing with something like this in life, this very interesting situation. We don't really want to be spending a lot of money necessarily because we might not have jobs in a month or two, or someone could end up getting ill and we need to help them. So it's even more important to understand what we're spending on a day-to-day basis, on a month-to-month basis, so that we don't end up with just lots and lots of debt. Okay. Homework due dates. I also extended 4.1 and the Excel file as well, which was also named budget, but it was a very different type of budget. I was very nice and extended that till tonight. So if you have not heard about that yet, this is you hearing about it. I did email it, but hopefully I can get as many people to complete those assignments as possible. I'm not going to be giving as many Excel files moving forward with this setup as homework. I'm still going to give some. You still have your project. I am definitely only giving one project now. That was in the plans already. I thought about giving a small second project, but it's just going to be the one for now. So you'll still have my math lab homework that's always going to be due a week after. So those due dates are going to continue to be the same. You're still going to have Excel homeworks that I will give you advance notice, at least a week's notice, as well as the due dates. These videos will be posted in, I'm going to upload them to YouTube and then post them in Canvas. So when you're in Canvas, hold on, let me get my screen share still up. So right now, the only thing that you'll see is this Zoom live lecture link, and that will always take us to the live lectures on Mondays and Wednesdays. But under that, when I finish closing this meeting out and I upload it to YouTube, once everything is on YouTube, I will post a link, so it'll be under lecture videos, and I'll call it Monday 323. I'll try and put the section titles in there as well, but that's all it's going to be in there. So if you ever don't have the opportunity to catch this class at 9:30 in the morning, you will still be able to see it. However, you really, really, really are expected to show up for the 9:30 class. When you show up, I get a participants list, so that's kind of the role. So if I have a student who's not moving forward with homework and I don't see them on the live chats, then I could say that that's them not showing up for class. And this is only going to be in extreme circumstances. You really, really do just need to make sure you watch all these videos. Don't skip around. I might do quiz questions in there and then ask you to submit them in Canvas or in my math lab or something like that. I'm still doing a lot of planning. We have the most interesting of my 5 classes, so I've saved us for last, unfortunately. But little rants aside, let us get into 4.2. So 4.2, which covers part to whole ratios. And this is something that we did describe a little bit in the past. So we've talked about, say, all right, there's 17% of students. Sorry, someone just asked a question. So if I work one of the mornings you go live, can I always just go back and watch it? Absolutely. That is exactly what this whole thing is for. So the recordings will be on YouTube permanently. And also, if you just go into YouTube, once you find my channel, it's something like RCB, TCC Math. It's something like that. And you don't have to look that up. Again, once I have a link there, it'll take you to my channel. I'm going to create a playlist in there as well. So whether you go through Canvas or just directly go to my YouTube, you'll be able to find those videos. So make sure you go to Math 154, not my other 4 classes. All right. So part to whole ratios. We talked about this a little bit in the past. Like we had something along the lines of 17% of people know enough math to work in an auto factory. Somewhere in that ballpark, it was a number. That is a part to whole relationship. That's 17 out of 100. So for every 100 people in the world, 17 of them know enough math to work in an automotive factory. So that part would be the 17, the 100 would be the whole, and it's 17 over 100 because I said percent. And back to the part to whole for percents, we said that a part over the whole is always the percent over 100. And as a reminder, the super, super important, something after the word of is the whole. And we saw that in those 4 examples. So the 230 in this example was the whole because it came after the word of. This 15 did not come after the word of, so it was not necessarily the whole, but it actually is because you have to use logic. It's not always the word of that says it. So, oh, there's no of, the 15 is, actually it is. Then here, of the earth, so the earth is covered in water, so the water would not be the whole, it's the earth that would be the whole because it came after the word of. All right, so part to whole and part to part are 2 different types of ratios. Sometimes we're talking about part to whole, sometimes we're talking about part to part. So let's say you've got 4 red marbles and 5 blue marbles. So there's 4 red marbles and 5 blue marbles. The part-to-part ratio for red to blue would be 4 reds over 5 blues. Now there's nothing that says that you have to do it as red over blue. So let me try something real quick. Or you could say that the blue to red ratio would be 5 blue over 4 red. And I apologize for my even worse handwriting. I'm using a pen and basically a digital drawing board, and I'm still getting used to it. It is what it is. So because I said 4 reds and 5 blues, I wrote 4 reds over 5 blues. We tend to write ratios in the order seen unless we're told to do otherwise. But if for some reason we didn't want to do it that way, we could say 5 blues over 4 reds. So these are parts. If I wanted to know a part-to-whole ratio involving the 4 red marbles and 5 blue marbles, so with these same numbers above, if I wanted to talk about the reds, then that ratio would be 4 reds to the 9 in total. Now, where did the 9 total come from? Down here in this bold. If you're given 2 parts, if you add part 1 and part 2, that's going to make the whole. That's only if you're given 2 parts. If you were given 3 parts, you'd have to add part 1, part 2, and part 3. But what that's convenient for, and this is only if there's 2 parts, you can always take the whole, subtract 1 part, and you'll get the other. And you can see that with the reds, the blues, and the totals. If you did 9 minus 4, you get 5, which is the blue. Or if you do 9 minus 5, you get 4, which is the red. So the 2 parts always add to the whole, or the whole minus 1 part would give you the other part. That's only if it's 2 parts. If there's 3 or 4 or 5 parts, this relationship would have to be the whole minus all other parts. It would just be a little more complicated, but the same idea. So you'll know whether you're doing a part-to-part or a part-to-whole ratio based on the problem, based on what they ask. So if I say, what's the ratio of reds to the total, it's 4 reds over 9 total. If I say, what's the ratio of reds to blues, it's the 4 over the 5. If I say, what's the ratio of the blues to the wholes, it's the 5 over the 9. And what's really awesome is you can still use a ratio table, but you're going to have to need columns for the parts and columns for the wholes as well. So you have to have columns for the parts and for the wholes. So let me try this. So let's go. What am I doing? This annotate thing is weird. I didn't mean to do that. That's okay. Starting over. If we have our reds, our blues, and our totals. Straight lines are hard with this thing. There we go. So the reds were the 4, the blues were the 5, and the total was the 9. Now, this is not a ratio table because it's just a single row of numbers. I would need to say that there's some type of relationship between another set of marbles. So then I could say, okay, well, what if there were 8 red marbles? So what if there were 8 reds and this whole thing was proportional? So you could put an X there to find the blues, and you can say that 4 over 8 is equal to 5 over x. You cross multiply, which would give us 4x is equal to 8 times 5, which is 40. You can then divide both sides by 4. And that tells us that x is equal to 10. So with 4 reds and 5 blues, if I have another set of marbles that are proportional, if there's 8 reds, that means there has to be 10 blues. Now you could find the total by adding the 8 and 10 and get 18. Or you could also just instead, and I'm going to call this T for total, you could instead go 4 over 8 equals 9 over T. So I'm not using the blue column. Remember, you can just imagine yourself drawing a box around your table where the 4 corners are your numbers and then a single blank. So 3 numbers in the corners, the 4, the 8, and the 9, and they're blank. So I skipped the blue row. So 4 over 8 equals 9 over T. So we cross multiply. We get 4T is equal to 8 times 9, which is 72. We can then divide both sides by 4. And guess what? 4 goes into 72 18 times. So if there were 8 red marbles and this was some type of proportional relationship, that means there would have to be 10 blues and means 18 total. That 18, again, that could have been found by adding them, or you can just use the idea of proportionality. Now, with marbles, do they have to be proportional? No, this would be much better for a problem that is implicitly proportional. Things like tax sales, products in stores, things like we've done in class. All right. So I need to go off annotate. Where was... oh boy. So that's going to stay on the screen. Let's clear that. So in our worksheets, in the section 4.2 part-to-part ratios, this is page 161 I'm on currently. They have a little summary. The most common interpretation of a percentage is a part-to-whole ratio. Indeed, many people define percentages as part-to-wholes, which can cause much confusion when dealing with other uses of percentages. If we were given the ratio of boys to girls in a class is 2 to 3, then it can be easy to mistakenly say the boys are 66.7% of the class, or even worse, 66.7% of the girls are boys. I think it's obvious that that last statement is incorrect. The correct statement is that the number of boys is 66.7% of the number of girls. So again, we're talking about 2 boys for every 3 girls in this class. There's 2 boys for every 3 girls in the class. That means that the boys are actually 40% of the class. So you've got 5 total, 2 out of 5, the part to whole, 2 out of 5 is 40%. So if you just go 2, wow, that was terrible. Use the pen, not the mouse. You went 2 over 5. That's the boys compared to the total. And if you just wanted to know this as a percentage of the class, then you go percent over 100. We don't know that, so we call it x. You would cross multiply and solve. You'd get 200 equals 5x. You divide by 5, and that tells us that x is equal to 40. So that says the boys are 40% of the class. Because we took the boys and compared them to the total, so the 40% is in reference to the total. But in this table right here, this 66, that's the math we just did was to get this 40 here, and that was when we scaled the total to 100. this 66.7 is talking about 2 out of 3. So let me just pretend like this number's not here for a second. Let's call that, how about B for boys? So if I just pretend like I'm doing here, we're scaling the girls to 100 because we're talking about the boys in comparison to the girls. So you go 2 over B equals 3 over 100, which will give us 200 equals 3B, dividing both sides by 3. Tells us that 66.7 rounding to the nearest tenth is equal to B, and that's where that number came from. So again, scaling the girls to 100, scaling apart to 100 is comparing the boys to the girls. We're comparing the boys to the girls because we scaled the girls to 100. We could have instead scaled the boys to 100, and they don't show that in the table, but I want to show that in addition in a few minutes. So again, the 66.7 is not saying that the boys make up 66.7% of the class. They're not making up 2/3 of the class. They're making up 2/5 of the class. So you have to be very careful. That's what they're talking about in this paragraph. You have to be careful of what you're referring to. If you're just dealing with the 2 and the 3 and not the 5, that's comparing a part to part. If you deal with the 2 and the 5, that's comparing a part to a whole. So scaling the whole to 100, that's where the boys came up with 40. And the girls being 60, it would have been the same math. You're just going 3 over x equals 5 over 100, or 2 over 5 equals, sorry, 3 over 5 equals x over 100. Sorry, I'm trying to move something. Give myself a little more room. I guess I don't really want to do that. Okay, there we go. I should have probably just used the whiteboard. I'm learning. So if you wanted to figure out the 60 number, let's pretend like the 60 is not there. Again, just using the idea of a ratio table, we can go 3 over, and we'll write a G there for girls. So 3 over G equals 5 over 100. Let me do that down here. 3 over G equals 5 over 100. Cross multiply gives us 300 equals 5 times G. That's a G, not a 6. Divide both sides by 5. And we can see that 60 is equal to G. So 60 is the percentage of girls of the class. 60% of the class is girls, 40% is boys, and there's your total of 100%. So boys, girls, students. Let me switch to the whiteboard. Let me share whiteboard. Boys, girls, students. Oop, didn't mean to grab that. So it's 2 boys, 3 girls, meaning 5 students total. So for every 2 boys, there's 3 girls. And we scaled the girls to 100 earlier and said that the boys came up to 66.7. So again, that statement is the number of boys is 66.7% of the number of girls. For every 2 boys, there's 3 girls. So for every 66.7 boys, there would be 100 girls. Now, what if we instead scaled the boys to 100? And now the girls is the unknown. Let's call this, let's just make this the letter A, so I'm switching letters up. So it would be best to use the 2 and the 3. They're easier numbers. So I'm going to pretend like the second row isn't there. Drawing our box around. This, and we're using the 2, the 3, the 100, and the A. So we'll go 2 over 100 equals 3 over A. And remember, you can do this 2 over 3 equals 100 over A instead. There's a lot of different ways you can write your proportions. Cross multiply, you'll get 2A equals 300. Divide both sides by 2, and you'll get that A is equal to 150. So that says that the girls, or the number of girls, I'm going to try and phrase this sentence the same as how we had it before. The number of girls is 150%, and it's percent because we scaled to 100, of the number of boys. So in other words, if there were 100 boys, there'd be 150 girls. Again, there's no statement about the total in there because in this table, we weren't using the total column. We used the total column earlier to get the 40 and the 60%. So again, when you scale the students to 100, that's when we came up with the 40 and the 60 that was seen in the original table here, the 40 and the 60. Oops, what did I just say? So what I'd like you to try and do on your own, and I'll show the completion of the first box, is this guided practice activity 1, parts of the population, dealing with census, which some of you may be getting census information right now. I know I just got mine. The following table gives sizes of the US population on July 1st, 2017. So there were 73 million and some change people under 18, 200 million from 18 to 64, 50 million and some change, 65 and over. So to get the total here, all you would have to do is add. I don't know why I keep using my mouse. Just add up the 73 million, the 201 million, and the 50 million. And that'll give you the total population as of July 1st, 2017. And then they want you to find all these other blanks. Well, to find these blanks, you just use a proportion table. So this first row under the totals, so let's call this row 2. So the second row, we have the 18 to 64-year-olds scaled to 100. So we're going to look at the other 2 portions of the population as a part-to-part relationship, where we're thinking about the 18 to 64, the biggest chunk of our country, being the 100%. So we're going to say that the 18-year-olds are this percentage of the 18 to 64s, under 18-year-olds is what I meant to say at first there. And then we'll be saying that the 65-year-olds are this percentage in comparison to the 18 to 64s. So if I call this letter, let me just call it A for now. So we would go 73 million and some change, 655,378 over A, and that's going to be equal to the 201,205,121 over 100. And you'll then cross multiply, which the 73 number will just get 2 zeros added on. So 73655,378,00 equals that 201,205, 121 times A. Divide both sides by the 201 million number. I'm going to pull out my calculator. I got to switch from annotate. So we're doing 736,553. 7800 divided by see that easier. 201, 205, 121. And we get 36.6 blah, blah, blah. So that's our answer rounded to 1 decimal, the 36.6. So we can go over here and say that 36.6 is equal to A. So that says that the people under 18 years old are 36.6% of the people of the size of the people 18 to 64. So again, the people under 18 years old are 36.6% of the value of the 18 to 64-year-olds. Not saying anything about the total. So then down here at the very bottom row, that's where the total scale to 100, that's where you'll actually figure out how much of the population these people make up. And again, I'm leaving this to y'all because you'll have to add those 73 million, the 201 million, the 50 million to get the total there. So that'll put a number in this block. And then you'd be able to use, say, the 73 million, the total, this blank, and the 100 to find out what this one is. So that would be our, I don't know, let's call that letter Z. It looks like a 2, but that's a Z. So I can find that without finding any of these other blanks. You still will have to find all these other blanks. So again, this is going to be your first discussion board, is to get the numbers that go in here. And then I need to get rid of that. Where's my clear screen? We're not going to do any of this concentration stuff. This is an Excel preview. And then we get into percent change and percent difference. So that's really all there is in 4.2. I don't know if y'all heard me drinking my water. Excuse me if you did. And that's not to say that anything in that was super short or super easy, but it is just using concepts we've already covered. Ratio tables, proportions, cross multiplication. The only thing that can be a stumbling point is going back to the, when you scale a non-total to 100, you might not say the correct thing. All right, so let's move on to 4.3. It's bigger. Percent change and difference. Percent change and percent difference. Percent change and percent difference. So total change, and sometimes you'll just see this as a dollar change, specifically if you're talking about money, or you might see it phrased as absolute change. So all three of these things mean exactly the same thing. Total change is absolute change. Total change is absolute change. Total change is absolute change. Total change is the difference in the two values. It's going to be positive if it's increasing, and it's going to be negative if it's decreasing. So change is always based on what occurs first. Well, I use the word always there, and I shouldn't, because you can consider change without time constraints, and we'll get into that a little bit later. But for now, total change is the difference of the new and the old. Total change is the difference of the new and the old. It's just a subtraction. This isn't some big crazy formula. I would call this a concept, as I would in class. So total change is just subtracting the new and the old. Change is a difference. unless you call it a percent change. Percent change is a relative difference. Also, you might see it listed as the symbol percent and then the word change. So relative change is percent change. Relative change is percent change. Relative change is percent change. So total change, again, is just the subtraction of the new and the old. It's always new minus old. If that number is positive, then it means things have gone up. So let's say a store sells 10 apples on Monday and 20 apples on Tuesday. That would be a percent change in an increasing manner. We haven't talked about how to find the percent change yet, but it would be a positive difference. You'd be doing 20 minus 10. Or we could say that a store sold 10 things of toilet paper before what's going on now, and then they sold 1,000 rolls of toilet paper after what's currently going on. And that would definitely be an increase, 10 versus, what did I say, 1,000. So increases are if things are going up, decreases are if things are going down. And again, total change, absolute change is just the difference of them. Percent change, which is arguably a more important idea, is all about scale. And we've talked about scale lots in this class. Scaling things to 100 makes it a percent, for instance. So percent change is the ratio, there's something we've dealt with, of total change to the original value. Now, these are, again, some people want to call them formulas. I call them concepts because a concept is one algebraic operation or one arithmetic operation, whereas a formula is like negative b plus or minus square root, blah, blah, blah. But you can still argue they're formulas. So these are not going to be on a formula sheet. You have to memorize these. You have to understand these. You have to know how to apply these. And I will admit that percent change is one of those things that people make very simple mistakes on constantly. Divide by the original. Some people just always divide by the smaller, or some people always divide by the larger. No, it has nothing to do with size in the bottom. It has to do with what happened first, the original. So it's the total change. How do you find the total change? It's up here. You just subtract the two things divided by what happened first. Now, an important final note, this is going to give you a decimal originally because you're just dividing two things. We didn't scale it to 100, so you have to convert it to a percent. Now, what you could do is call the top a part, the bottom a whole, and set it equal to percent over 100. It's literally the same thing as just moving the decimal right twice. So example 1. Let's talk about this together. Mr. Beckner had 20 students in his 11 a.m. class, Tuesday, Thursday class. This year he has 30. I should have changed that to Wednesday, but you get the idea. And we've also lost some students since then. Since I wrote this problem down, what is the total and percent change? So all this other stuff, let's worry about that in a little bit. So we had 20 students last year. This year we have 30. So let's pull up our whiteboard. Let's go to a new page. I'm going to use that whiteboard a lot more generally. It's just kind of nice to write on the screen when we have the worksheets out. So in the past, I believe we had 20 students. Excuse me. In the present, I think we had 30 students. I'm gonna double check those numbers real quick. Yes. And we wanted to know what the total change and the percent changes are. So again, the total change is just a difference. It's the difference of the new and the old. New minus old, new minus old, new minus old. The new being the 30 students minus the 20 students, which is 10 students. Now this is positive, so this would be an increase. If we had started with 30 in the past and had 20 in the present, we'd be doing 20 minus 30, which would be negative 10, signaling that it would be a decrease. And again, it should be fairly obvious whether it's an increase or decrease. Just look at the numbers, pay attention to what happens first. But there's those two words we always hear over and over. We have to pay attention. So our total change is the 10 students. And that was an increase. The percent change is again the ratio of the total change. I'll write this formula to the original, not the smallest, not the largest, the thing that happened first. The total change we just found to be 10 students. The original, was that the 20 or the 30? The 20 or the 30? Well, they said last year it was 20 students, so that's the original. Oops. Undo. There's my color, it's under format. Now I know that for later. 20 students. And look at that, by writing our units like we're supposed to, all the details are there. We have the same thing on top of each other, so the units cancel. 10 over 20 is just 1/2, or 0.5 as a decimal. And there's no units to this, it's unitless. So the ratio of the total change to the original is 0.5, but that's not a percent. We have to convert. And 0.5, moving the decimal right twice, becomes 50%. And this again is a 50% increase. So there was a 50% increase in class size. Now you might think, oh, it's supposed to be 150% because we went from 20 to 30, and 30 is 150% of 20. But percent change is not just taking a percent of something. It's talking about comparing an old and a new value. Sorry, I just got a really loud email sound. I don't know if y'all heard that or even saw it. I got distracted. So again, percent change is about relative to what has happened in the past. So there's 10 more students in this newest class, and 10 is half of 20. That's why it's a 50% increase. If you flip this around, let me flip this around, and let's say if we reverse the scenario, let's say the past was the 30 and the present was the 20, then the total change would be 20 minus 30, which is negative 10. So that means we lost 10 students. And the percent change would be negative 10 over the original, which is now 30, which reduces to a third, and that's students over students, so they still cancel. So that's negative 1/3, which is negative 0.33333, which as a percent would be negative 33.3%, and that's a decrease. So if we had gone from 30 to 20, it's a 33% decrease, whereas going from 20 to 30, it's a 50% increase. So the order of the numbers has a drastic effect on the percent change. The total change doesn't really feel like that drastic of a change. I shouldn't use that word, because it was 10 students as an increase before, now it's 10 students as a decrease. So it's still the same absolute change, just up or down, but a percent change being based on the original, if the original is smaller, it makes the percent change bigger. If the original is bigger, it makes the percent change smaller, because when we divide by bigger numbers, it makes the output smaller. We discussed that a couple of weeks ago in class. I think it was one of the last things we did in chapter 3, where we had that what if analysis. So again, percent change is heavily based on the original. And when you see your stocks going up and down, a 1% increase and then a 1% decrease does not put you back at the same thing for the same idea, because each time the original is different. So that might be an interesting thing to think about. If your stock goes up 1% and then it goes down percent day to day, would you end up with the same amount of money, more money, or less money than you had at the very first day? And I'll say it's not the same, but I want y'all to think about whether it would be more or less. Maybe you can do the math with that somehow. Start out with an example. Say you have $100. If it goes up 1%, you then have $101 after that. And then when it goes down 1%, and then I won't spoil the rest of it. Okay. So we need to go back to my screen. Arrow notation. So this arrow notation that you'll see in your text. Sorry, moving things around. This is this super important part is not in relation to the arrow text. So arrow notation, what exactly is this? Again, we're focusing on this arrow notation. Back to the whiteboard, new page. Arrow notation. You're going to have something that looks like this. It's going to be a number, the old number, then you'll have a long little arrow, and then you'll have the new number. Above it, you might have like a positive or a negative number. This is going to be the total change. And below it, you might have a number with a percent sign. This will be your percent change. This is notation. This is not a formula. This is just notation. So for that last problem that we were working on, we started with 20, and then we bumped up to 30. So example 1, in this notation, it looked like this. We started with 20 students, and then we end up with 30 students. So the old is on the left, the new is on the right. It's like the old is pointing to the new. I've honestly never seen this notation anywhere else except this text, but we have to introduce it because you're going to see this a few places. You'll see it in homework, you'll see it in the worksheets. So we figured out that the total change was an increase of 10 students, and you might not see the units there. And then the percent change, we said it was a 50% increase, so plus 50%. So again, we started with the 20 and the 30 as part of the problem. We found the total change as 10, and it was an increase, so we write that as a plus sign. We found the percent change to be 50% as an increase, so we use that as a plus sign. I'm never going to ask you on a test to write things out in arrow notation. You'll be expected to pull information from that. So in other words, let's call this example. Do I want to call it example 2? I can just change numbers later. We'll call it example 2. And we'll just say, use the arrow notation to describe all info. So let's say someone's stockpile of toilet paper, this is relative, they went from 5 rolls on the left, they got 50 rolls on the right. And then this would be let's fill in the rest as well. So 5 and 50. So because the 5 is on the left, that means that the old is 5 roles. Since the 50 is on the right, the new is the 50 roles. To find the total change, which would go up here on the top of the arrow, I'm going to abbreviate with total change, TC. That would be 50 roles minus 5 roles, which is 45 roles, and that's an increase. The percent change, we take the total change, which is the 45 roles that we just found. We divide it by the original, which is 5 roles. So our roles cancel. 45 divided by 5 is 9. But that is a percent, it would be 900%, and that's an increase. So now the arrow notation looks like 5 roles, pointing at 50 roles. We found the total change to be a positive, an increase of 45. And again, you may or may not see the units there. And then the percent change we just found to be 900%, and that's an increase. So we'd write the plus sign. Now what's interesting is we don't have to give you, oops, I didn't mean to write that. We don't have to give you the old and the new and ask you to find the total change, the percent change. We can give you the new and the total change, and you can find the old change, the old, excuse me, by subtracting them. So what if I gave you this as a problem? And I said the change was 45 roles. So I don't know how many we had in the past, but I know that we just bought 45 rolls. And then when we got home and we put the 45 rolls wherever we're keeping them with the original, we count 50. So now we can calculate the original by doing the new minus the change, the total change, which would be 50 minus the 45, and we get 5 rolls. So it's the same problem. You can also do this with the percent change, but we haven't talked about the formulas involving that yet. We're about to. I just saw that someone asked a question in the chat about 10 minutes ago. Sorry about that. So it's 50% more of the original. Yes, going back to the 20 moving to 30, there's 50% more students. So half of 20 is 10, that's the 50, and then you toss them in as well to the class. Cool, if I didn't already answer that implicitly. Now we need to move on to something that is super important. It's underlined, it's bolded, it's got like 10 exclamation marks after it. This is I would call this a formula for the growth and decay factor part. But again, you have to memorize this. A growth or decay rate, let's say we called it X, where it would be a percentage. So a growth or decay rate, that's a percent change. It's a growth if it's an increase. It's decay if it's a decrease. So again, it's growth if we're increasing, and it's decay if decreasing. Sorry, more emails. I gotta turn that notification off when I'm doing this. So if we call the growth or decay rate X, so 5%, 10%, the 5 or the 10 would be our X. This thing known as a growth or decay factor would be 1 and then plus or minus the percentage. The X is a decimal, or 100% plus it if you have it as a percent. So again, if you're using the 1, you would have the percentage as a decimal. Sorry, I thought I had annotate on. So it'd be or 100 plus or minus the x as a percentage. So that's a growth or decay factor. It's growth if it's an increase, so you choose the positive. It's decay if it's a decrease and you choose the negative. You're never going to use the plus and the minus. You're going to use one or the other. This, again, is going to be super important. This leads us into chapters 5, 6, 7, 8, and 9, which we don't do 7 anymore. But this is going to stick with us with this equation right here. New equals the original times 1 plus or minus the percent change, where the percent change is listed as a decimal. New equals original times the growth or decay factor. That's the same thing, because that parentheses with the 1 plus or minus x percentage, that is the growth or decay factor. The original is what we've been calling old, original, those are interchangeable words. So this is the old times the growth or decay factor. New equals old times growth or decay factor. New equals old times the growth or decay factor. When your stocks increase or decrease, how do you find out how much you have the next day? You take the old and you multiply it by the growth or decay factor. Growth if it increased, decay if it decreased. If you get a salary increase, your boss gives you a pay bump and he says, I'm going to give you a 2% pay bump. How do you find your new salary? You take your old salary and you multiply it by your growth or decay factor. If I know that my students are going to decrease by 15% because of this new format, I can figure out how many students I have now by taking, you guessed it, how many students I used to have times the decay factor. And then I point out down here that you could also be given the new or the original and be asked to solve for the either. You don't have to be given the original and the percent change. You could be given the new and the percent change. You could actually be given the new and the original and find the percent change based on this formula. But that's a little more complicated than we want to do. All right, I'm only going to talk for a few more minutes. I want to do at least one of these examples, and then we will move on. Oh, I got to clear the screen. So this will be example 2. Now it's 3. And I'll show these for now. Let's just make this one bigger. Your old salary in 2018 was $55,000. Your boss gives you a 7% COLA, that's a cost of living adjustment, and attaboy pay raise. What is your new salary? So cost of living right now is not going up 7% per year, although I say that, but with the dynamics we're in, maybe it will. But let's just say for the past 10 years, cost of living adjustments have been about 2 or 3% generally, because that's what inflation is. So if you have a job that gives you cost of living adjustments every year, you get inflation added to your pay every year. So if inflation is 2%, your cost of living adjustment is 2%. If inflation is 3%, your cost of living adjustment is 3%. The attaboy is someone's done a good job. So if the cost of living adjustment was 2%, that means they got a 5% pay increase as well for doing a good job. But again, all that stuff, not the point of the problem. The point is, what is the new salary? So we were making $55,000. That was the old salary. That's the original salary. We got a 7% increase. Pay raise means increase. So let's go to another screen. So the original, I forgot I can type in here as well, was 55,000. Then our percent increase, that was the 7%. So the growth factor. I didn't actually ask for this, but let's just show it anyways. Remember, that's 1, and it's going to be plus the x percent, but this is as a decimal. So that would be equal to 1 plus 0.07, which is 1.07. As a percentage, if you wanted to see it, that would be 1 plus the x percent as a percent. Sorry, not 1, 100. Pardon my foul. So that would be 100 plus 7, which is 107%. So this right version is the best way to think about it. Our new salary will be 100% of the old salary. The new is 107% of the old. And the word of means to multiply in algebra most of the time. I know we talked about it with proportions, with the percent problems and how it told you what was in the bottom. But in just basic algebra, not in proportions, of generally means time. So we're taking 107% times the old value. We don't deal with percentages in equations, generally speaking, which is why the 1.07 is the better number to use. So the growth factor is 1.07. If we take our old salary and multiply it by the growth factor, we get the new salary. So again, new equals old times, wrong letter, the growth factor. So the new should be 55,000 times, and I'm going to write it in the full parentheses, the 1 plus the 0.07, because I know a lot of people aren't going to do the growth factor ahead of time. But again, this 1 plus 0.07 is the same 1.07 we had before. That's $55,000 times 1.07. And if you pull out a calculator, I'm not going to switch my screen, you'll end up with $58,850. So your new salary is $58,850. And that makes sense. Remember, you're always making sense of your answers. If I had subtracted the 0.07, you'd end up with an answer that's less than $55,000. And that wouldn't make sense because you got a pay raise, not a decrease. Maybe you multiply the whole thing by 107 instead. So if you took 55,000 times 107, you would end up with 5,885,000. And that would not make sense because a 7% pay raise is not going to take you from 50 grand to 5 million. So again, make sense of your answers. It's very, very important, especially when you get to some of the other problems. Oops. I hope I didn't just mess something up. So here are some other examples. And we're not going to have time to cover these. Your new salary is $71,500. You just earned a 10% pay raise. What was your old salary? So you can still do this with the same formula. You're just going to have a little bit of algebra to solve. But I want to leave that for next class. I don't think we can do that in just a few minutes. So on that note, we will call it a day. We have almost finished 4.3, but we definitely finished 4.2. So let's go back to the whiteboard. Whiteboard. So your assignments. 4.2 is due in a week, which would be the 30th, I believe. Yes. By 11:59 p.m., of course. And then we'll finish 4.3 next class. So that makes that due on April 2nd, April 1st. I don't know what happened there. 11:59 p.m. So I'll get those updated in my Math Lab shells soon. Again, this video has hopefully been recording. So assuming that it has, I will be posting the recording in YouTube. I'll upload it after class, and hopefully it will be in Canvas in the next 15 to 20 minutes. If it takes a long time for the video conversion to handle, because I haven't done this with an hour long, I've only tested it 15 minutes at a time. So it might take a little longer. If for some reason the video isn't posted by today, I'll shoot an email out, but I'm pretty sure I should be able to have it up in the next hour. If you have any questions, shoot me an email. Thank you all very much for dealing with this new format. I am, of course, sorry that we had to do this change, but this is better than nothing, and we will make the best with what we have. So have a good day, and I will see you all Wednesday morning. Fingers crossed this records. Stop share. End meeting.